Now, of course, that integral we just did was over a box, but there's no reason why we have to only integrate over boxes. We can also integrate over different three-dimensional regions. So let's say we have some region E. We first need to talk about what the axes are, and we'll usually draw them like this, with x coming out of the page like this, in this direction, y going this way, and z going up. Then when we set up the bounds on our integral, we're going to think of x as going from the back to the front. So positive is direction of x is the front, and negative is the back. Then y is going left to right. So this is negative y, this is positive y. And then z is going to go from the bottom to the top. So down here is negative z, up here is positive z. So that's what we'll do with our axes. Let's look at an example. Let's set up a triple integral to compute the volume of the region E, where E is the tetrahedron that's bounded by the planes x equals 0, y equals 0, and z equals 2, and x plus y plus z equals 4. So what does x plus y plus z equal 4 look like? It's a plane that intersects these axes at 4, 4, 4, and 4. So the tetrahedron itself is going to look something like this. But then we're bounding it by the plane x equals 0, which is this plane, the plane y equals 0, y equals 0, which is this plane, x equals 0, which is this plane, and then z equals 2. So we're cutting it off at z equals 2. This is the top. So it's really going to look slightly different. We're going to cut off this top half. Of the tetrahedron, since we're bounding it at z equals 2. And so it'll look something like this. It's like a tetrahedron with the top cut off. Let me redraw this line a little straighter. So this is what our region is going to look like. And we want to find the volume of this region. That's the same thing as integrating 1 over this region. So our integral is going to look like a triple integral. And we need to pick an order to integrate in. I'm going to say let's integrate with respect to y first, because why not? And we'll do y, then maybe x, then z. And we're going to integrate 1. This will give us the volume. Now all we need is our bounds, and that'll give us this whole integral, which will help us to calculate the volume of this figure. So first we need to find the bounds on y. Well, what can y be? Y can be anywhere as low as 0, but then once it goes this way, it runs into this wall of the tetrahedron. So it can go anywhere from 0 to this wall of the tetrahedron. So the smallest bound is 0 for y. So then the largest, whatever this wall is, well, we know the equation of this plane. It's x plus y plus z equals 4. So if we want to know the maximum value for y, we just solve for y in this equation. And we get y is equal to 4 minus x minus z. So the largest y can be is 4 minus x minus z. So that gives us our upper bound here. So what do we do next? We found our bound for y. In general, how we do triple integrals, we find our bounds for the first variable we're integrating with respect to. Then we project our figure onto the plane of the other two variables. So we've already done y. We're going to look at what this looks like when it's projected onto the xz plane. So here we're only thinking about this region right here. And so let's draw this again so we can figure out better what it looks like. If we draw the xz plane, where this is z, and this is x, This is positive x and negative x. Then what it looks like is something like this, where this is intersecting at x equals 4, and this is z equals 2. So it's a trapezoid right here. So this is our figure. Now we just need to describe the bounds on x and z that describe this region. And so we're going to do x first. X can go from 0 all the way up to this line, whatever it is. So 0 to this line. And how do we describe this line, this upper bound? Well, what is this line? Again, this line is coming from the plane, but it's coming from right here, the plane where y equals 0. So if we just look at this equation, x plus y plus z equals 4, at y equals 0, y becomes 0, so we have x plus z equals 4. That's the equation of this line right here, x plus z equals 4. Or we could look at points in this plane and figure out the equation. But we're going to get the same thing either way. So we want to know what is the x value on this line. Well, using this equation, x is just 4 minus z. So x goes from 0 to 4 minus z. So that's our upper bound for x. Then finally, since we have our bounds for y and x, we just need to find our bounds for z. Well, z starts at 0 and then goes all the way up to 2 all the time. So these bounds are simple. It's just the integral from 0 to 2. And so this whole integral gives us the volume of this cutoff tetrahedron region.